You're currently traveling faster than any human-made object in history, and you have absolutely no idea where you're going. Something out there is pulling us faster and faster, and we're only beginning to understand. And here is a question. If you could witness any moment in cosmic history, what would it be? The Big Bang, the first star, or perhaps something else? Let us know in the comments. I will pin the most creative answer. Now let's begin. The story of our cosmic motion is one of the most mind-bending discoveries in the history of science. For thousands of years, humans believed the Earth stood perfectly still at the center of everything. The stars, the sun, the moon, they all seemed to revolve around us. It made sense. Nothing felt like it was moving, but then something changed. Brave thinkers began to question what seemed obvious, and what they discovered shattered our understanding of reality itself. Let me take you on a journey through the layers of motion that carry you through space. We'll start small, with the ground beneath your feet, and build outward until we reach the edge of the observable universe. Each layer reveals something astonishing about our place in the cosmos, and I promise you, by the end of this video, you'll never look at the night sky the same way again. First, let's talk about something so familiar you probably never think about it: the rotation of the Earth. You see, our planet spins on its axis once every 23 hours, 56 minutes, and 4.09 seconds. That's what astronomers call a sidereal day. It's slightly shorter than the 24-hour day you're used to because the Earth is also moving around the Sun, which adds a few extra minutes to bring the Sun back to the same position in the sky. Now here's where things get interesting. The Earth's circumference at the equator is about 25,000 miles, or roughly 40,000 kilometers. If you're standing at the equator, you need to cover that entire distance in just under 24 hours. Do the math, and you're moving at approximately 1,000 miles per hour. That's faster than the speed of sound. You're breaking the sound barrier just by standing still. But wait, there's more to this story. The speed depends on where you are on Earth. If you're closer to the poles, you're moving slower. At the North or South Pole, you're barely moving at all, just slowly rotating in place. This is because the circumference gets smaller as you move away from the equator. Someone in London, for example, is spinning at about 650 miles per hour. Someone in New York, about 790 miles per hour. The farther south you go toward the equator, the faster you're spinning. This difference in rotational speed has real consequences. It's why space agencies prefer to launch rockets near the equator. NASA's Kennedy Space Center in Florida benefits from that extra eastward speed boost. The European Space Agency launches from French Guiana in South America for the same reason. When you're already moving at over 1,000 miles per hour, you get a free velocity boost that saves fuel and makes it easier to reach orbit. But here's the beautiful paradox: you don't feel any of this motion. Why? Because everything around you is moving at the same speed. The air, the ground, the buildings, the trees, they're all spinning together. There's no wind in your face, no sensation of movement. It's like being on a perfectly smooth train. As long as the train moves at a constant speed without bumping or turning, you can't tell you're moving at all. Earth's rotation is that smooth train carrying you effortlessly through space. And if you're enjoying this cosmic journey so far, please give this video a like and subscribe to the channel. It helps more people discover these incredible facts about our universe. Now let's zoom out and look at the next layer of motion: Earth's orbit around the Sun. Forget about spinning for a moment. Our entire planet is racing around the Sun at a speed that would make any race car driver weep with envy. We're talking about roughly 67,000 miles per hour, or about 107,000 kilometers per hour. That's nearly 70 times faster than a bullet fired from a rifle. Think about that for a second. Every single second, you're traveling about 18.5 miles through space. In the time it takes you to read this sentence, You've moved over 100 miles along Earth's orbital path. It's almost impossible to wrap your mind around. And yet your coffee sits perfectly still on your desk. The reason we move so fast is gravity. The sun's immense gravitational pull is constantly trying to pull Earth straight toward it. But Earth isn't just sitting there, it's moving sideways at tremendous speed. These two motions, the inward pull of gravity and the sideways motion, create a balance. Earth is perpetually falling toward the sun, but also perpetually missing it. That's what an orbit is, a carefully balanced fall. Earth's orbit isn't a perfect circle, though. It's an ellipse, a slightly stretched circle. This means our distance from the sun changes throughout the year. When we're closest to the sun in early January, a point called perihelion, we're about 91 million miles away. When we're farthest in early July at aphelion, we're about 94.5 million miles away. Because of this, our orbital speed varies slightly. We move a bit faster when we're closer and a bit slower when we're farther away. It's one of those cosmic quirks that makes the universe endlessly fascinating. Over the course of 1 year, Earth travels an astonishing 584 million miles around the sun. That's the distance light travels in about 52 minutes. And we do this journey every single year without fail, pulled along by the invisible hand of gravity, gliding through the vacuum of space at tens of thousands of miles per hour. But Earth isn't alone in this journey. The Moon is coming along for the ride, orbiting Earth while Earth orbits the Sun. The entire Earth-Moon system is barreling through space together. And so is every other planet in our solar system, each moving at its own speed, each dancing to the rhythm of the Sun's gravitational symphony. Now brace yourself, because we're about to zoom out even further. Everything I've just described, Earth's rotation and its orbit around the Sun, that's only the beginning. The Sun itself isn't standing still. Our star, along with all its planets, moons, asteroids, and comets, is hurtling through the Milky Way galaxy. And the speed, it's absolutely staggering. The Sun orbits the center of the Milky Way galaxy at a speed of approximately 447,000 miles per hour. Let that sink in for a moment. Nearly 500,000 miles per hour. That's roughly 514,000 miles per hour, according to NASA's latest measurements, or about 829,000 kilometers per hour. We're not just moving through space, we're screaming through it. Our entire solar system is located in what astronomers call the Orion Arm, sometimes called the Orion Spur. It's a minor spiral arm of the Milky Way situated between two much larger arms, the Perseus Arm and the Sagittarius Arm. We're about 26,000 light-years from the galactic center, roughly halfway between the center and the outer edge of the galaxy. From our vantage point, we're just one small neighborhood in a city of stars. The Milky Way itself is enormous. It contains somewhere between 200 billion and 400 billion stars. Some recent estimates push that number even higher. The galaxy spans about 100,000 light-years from edge to edge. That means even traveling at the speed of light, it would take you 100,000 years to cross it. And we're orbiting within this cosmic disk at nearly 500,000 miles per hour. But here's what really blows my mind. Even at that incredible speed, it takes our solar system approximately 230 million years to complete just one orbit around the galactic center. Astronomers call this period a cosmic year or a galactic year. Think about what that means. The last time our solar system was in this exact position in the galaxy, dinosaurs hadn't even appeared yet. Earth was in the Triassic period. The first dinosaurs were just beginning to evolve. One cosmic year ago, the world was unrecognizable. Since Earth formed about 4.5 billion years ago, our solar system has made roughly 20 trips around the galaxy. 20 cosmic years. Each journey takes us through different regions of the Milky Way, past different stellar neighborhoods, through varying densities of gas and dust. We're on an endless cosmic road trip, and we've been traveling for billions of years. Now you might be wondering, what's pulling us around the galaxy? What force is powerful enough to drag our sun and all its planets at nearly 500,000 miles per hour? The answer is both beautiful and mysterious. It's the combined gravity of all the matter in the Milky Way, including something we still don't fully understand called dark matter. You see, when astronomers calculated how far stars should be orbiting based on the visible matter in the galaxy, the numbers didn't add up. Stars on the outer edges of galaxies were moving way too fast. They should have been flung out into intergalactic space long ago, but they weren't. Something invisible was holding them in place. That something is dark matter, a mysterious substance that doesn't emit, absorb, or reflect light. We can't see it directly, but we know it's there because of its gravitational effects. In fact, dark matter makes up about 85% of all matter in the universe. Everything we can see, every star, planet, and galaxy, is just the tip of the cosmic iceberg. Speaking of speed, if you want to truly appreciate just how fast we're moving, I highly recommend checking out my other video called The Terrifying Truth About How Fast the Speed of Light Really Is. It'll give you a whole new perspective on cosmic velocities and why nothing can break that ultimate speed limit. The link is in the description. But let's keep going because, believe it or not, we're still not at the full picture of our motion through space. The Milky Way itself isn't sitting still in the universe. Our entire galaxy is moving through space, pulled by gravitational forces on scales almost too large to comprehend. The Milky Way is part of what astronomers call the local group, a collection of more than 50 galaxies bound together by gravity. The local group spans about 10 million light-years across. Our closest major galactic neighbor is the Andromeda Galaxy, also known as Messier 31 or M31. Andromeda is about 2.5 million light-years away, and here's something incredible. It's moving toward us. That's right. While the universe is expanding and most galaxies are moving away from each other, Andromeda and the Milky Way are on a collision course. They're approaching each other at about 250,000 miles per hour, or roughly 400,000 kilometers per hour. In about 4.5 billion years, these two massive galaxies will collide. Don't worry though, the collision won't be catastrophic for individual stars. Galaxies are mostly empty space. Stars will pass by each other like ships in the night, but the galaxies will merge, creating a new, larger elliptical galaxy. Some astronomers have already given it a name, Milkomeda. The local group itself is falling towards something even larger, the Virgo cluster, a massive collection of over 1,300 galaxies located about 65 million light-years away. The Virgo cluster contains so much mass that its gravity influences everything around it, including our local group. We're being pulled toward it at approximately 225 miles per second, or about 810,000 miles per hour. But that's not all. Beyond the Virgo cluster lies something even more mysterious and powerful, the Great Attractor. This is a gravitational anomaly located roughly 150 million light-years away in the direction of the constellations Hydra and Centaurus. The Great Attractor is pulling not just our galaxy, but thousands of galaxies in our local region of space. Its mass is estimated to be tens of thousands of times greater than the Milky Way. For years, we couldn't see the Great Attractor directly because it lies behind the zone of avoidance, a region of the sky obscured by the dust and gas of our own Milky Way. But using X-ray and radio telescopes, astronomers have been able to peer through the dust and map the structure of this cosmic giant. What they found is astonishing. The Great Attractor is part of an even larger structure called the Laniakea supercluster. Laniakea is Hawaiian for immeasurable heaven, and it's an appropriate name. This supercluster contains about 100,000 galaxies spread across 520 million light-years of space. The Milky Way sits on the outskirts of Laniakea, flowing along cosmic currents of gravity toward the supercluster's center. We're like a leaf floating in a river, carried along by currents we can barely detect. And here's where things get truly mind-bending. Even with all these layers of motion, the rotation of Earth, the orbit around the sun's journey around the galaxy's motion toward Andromeda, our fall toward the Virgo cluster and the Great Attractor, we still haven't reached our absolute motion through space. There's one more layer, one final reference frame that reveals our true speed through the cosmos. It's called the Cosmic Microwave Background, or CMB for short. And it changes everything. The cosmic microwave background is the oldest light in the universe. It's the afterglow of the Big Bang, radiation that has been traveling through space for over 13.5 billion years. When the universe was about 380,000 years old, it cooled enough for atoms to form. Before that moment, the universe was a hot, dense soup of particles and radiation, too energetic for atoms to exist. But when atoms finally formed, light was freed to travel through space. That light has been journeying ever since, stretched and cooled by the expansion of the universe into microwaves. The cosmic microwave background permeates all of space. It's everywhere, a faint glow with a temperature of just 2.725 degrees above absolute zero. We can't see it with our eyes, but sensitive instruments can detect it. And when we measure this radiation carefully, something remarkable appears. When scientists first measured the cosmic microwave background in 1965, they expected it to be perfectly uniform in all directions. After all, if it's the remnant of the Big Bang, it should look the same no matter where you point your telescope, right? But that's not what they found. Instead, they discovered something unexpected, a dipole pattern. Imagine looking at a map of the entire sky, color-coded by the temperature of the cosmic microwave background. In one direction, toward the constellation Leo, the radiation appears slightly hotter, shifted toward the blue end of the spectrum. In the opposite direction, toward the constellation Aquarius, it appears slightly cooler, shifted toward the red end. The temperature difference is tiny, only about 3.4 millikelvin, or 0.003 of a degree. But it's there, and it's significant. This pattern isn't a property of the universe itself. It's a Doppler effect caused by our motion through space. Just like the pitch of an ambulance siren changes as it moves toward or away from you, light and radiation change frequency based on relative motion. When we move toward a source of radiation, its wavelength gets compressed, making it appear hotter and bluer. When we move away, the wavelength stretches out, making it appear cooler and redder. The cosmic microwave background gives us something incredibly rare, a universal reference frame. In most of physics, there's no such thing as absolute motion. You can only measure how fast you're moving relative to something else. But the CMB is so ancient and so evenly distributed throughout space that it provides a kind of cosmic yardstick. By measuring the dipole pattern, we can determine our absolute velocity through the universe. And the answer? According to the most precise measurements from the Planck satellite mission, completed in 2018, we're moving at 369.82 kilometers per second, plus or minus just 0.11 kilometers per second. That translates to roughly 827,000 miles per hour, nearly 1 million miles per hour through the fabric of space itself. Think about that number for a moment. 827,000 miles per hour. That's fast enough to circle the Earth in less than 3 minutes. It's more than 1,000 times faster than the speed of sound. And yet, you're sitting there, completely unaware, feeling absolutely nothing. The precision of this measurement is extraordinary. Scientists can pinpoint our velocity to within less than 1 kilometer per second, an accuracy better than 0.03%. The direction of our motion is equally fascinating. We're traveling toward a point in the sky located in the direction of the constellation Hydra, near the border with Centaurus. The exact galactic coordinates are longitude 264.021 degrees, latitude 48.253 degrees. This direction isn't random. It reflects the combined result of all those layers of motion we discussed: Earth's orbit, the Sun's galactic orbit, the Milky Way's motion toward Andromeda, our fall toward the Virgo cluster, and the pull of the Great Attractor. When you subtract out Earth's orbit around the Sun, which contributes about 30 kilometers per second, and the Sun's orbit around the galaxy, which adds about 220 kilometers per second, you're left with the local group's motion through space. The local group, which includes the Milky Way, Andromeda, and dozens of smaller galaxies, is moving at approximately 627 kilometers per second relative to the cosmic microwave background. That's over 1.4 million miles per hour. This raises a profound question. Why are we moving so fast? What's driving this motion? The answer lies in the large-scale structure of the universe itself. The cosmos isn't smooth and uniform. It's a vast cosmic web of galaxy clusters, filaments and voids, all interconnected by gravity. We're being pulled along flows in this web like a swimmer caught in an ocean current. Astronomers have mapped these flows using sophisticated surveys of galaxies and their motions. What they've discovered is breathtaking. The Laniakea supercluster, which contains our local group, is itself flowing toward an even larger concentration of mass, called the Shapley supercluster, located about 650 million light-years away. This structure contains some of the most massive galaxy clusters in the observable universe. Its gravitational influence extends across billions of light-years. But here's where things get even more interesting. Recent observations have revealed something puzzling. When scientists measure the motions of galaxy clusters across huge volumes of space, they find that the universe appears to have bulk flows, large-scale motions that extend farther than our current models predict. Some clusters seem to be moving in coherent streams across hundreds of millions of light-years, as if being pulled by something beyond what we can see. This has led some researchers to wonder if there might be massive structures beyond our observable universe, structures so distant their light hasn't had time to reach us yet, but whose gravitational influence can still be felt. It's a tantalizing possibility, a reminder that the observable universe, as vast as it is, might be just a small fraction of the total cosmos. Now let's pause and consider what all this motion means for our understanding of the universe. For most of human history, we believed we were at the center of everything stationary and special. Copernicus showed us that Earth orbits the Sun. Galileo confirmed it with his telescope. Later, we discovered that the Sun is just one star among billions in our galaxy. Then we learned that our galaxy is just one among billions in the observable universe. Each discovery has been a step away from the idea that we're special or central. And yet there's something beautiful about our cosmic motion. We're not standing still. We're participants in the grandest journey imaginable, carried along by gravity and momentum across billions of light-years of space. We're sailors on a cosmic ocean, and the currents run deep. Every atom in your body has been on this journey. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was forged in stars that lived and died billions of years ago. Those stars were moving through the galaxy just as our Sun is now. The atoms scattered into space when those stars exploded, drifting through nebulae and molecular clouds until gravity brought them together to form our solar system 4.5 billion years ago. Since then, those atoms, now part of you, have made roughly 20 trips around the Milky Way. They've traveled through spiral arms and past stellar nurseries where new stars are being born. They've witnessed supernovae and navigated through clouds of interstellar dust. And now here they are, arranged in the miraculous pattern that is you, watching a video about cosmic motion on a tiny, rocky planet orbiting an ordinary star. This perspective, this cosmic viewpoint, is what makes astronomy so powerful. It connects us to something larger than ourselves. It reminds us that we're not separate from the universe. We're part of it. We're made of stardust, quite literally, and we're moving through space on a journey that began with the Big Bang itself. But our motion through space raises another fascinating question. If we're moving at nearly 1 million miles per hour through the cosmic microwave background, does that mean there's such a thing as absolute rest? Is there a reference frame where you could be truly still? The answer is both yes and no. Yes, you could theoretically adjust your velocity so that you're at rest relative to the cosmic microwave background. If you did that, you'd see the CMB dipole disappear. The radiation would appear uniform in all directions. In that sense, you'd be at rest in the reference frame of the early universe. But here's the catch. You'd still be moving relative to everything else. You'd be hurtling away from the sun at 67,000 miles per hour as Earth continued its orbit without you. You'd be racing away from the galactic center at nearly 500,000 miles per hour as the solar system continued its journey. The very concept of being at rest is relative. There's no universal stillness, no cosmic parking spot where everything stops. Einstein taught us this over a century ago with his theory of relativity. Motion is always relative to something else. There's no privileged reference frame, no absolute standpoint from which to measure all motion. The cosmic microwave background comes close. It's the oldest and most uniform thing we can measure, but even it's part of an expanding universe that has no center and no edge. This brings us to one of the most profound insights in modern physics. The universe has no center. The Big Bang didn't happen at a point in space that we can point to and say, there, that's where it all began. Instead, the Big Bang happened everywhere, simultaneously. Every point in space was once part of that infinitely hot, infinitely dense beginning. Space itself has been expanding ever since, carrying galaxies apart like raisins in rising bread dough. So what happens when you add up all these different velocities? What's our total speed through space? This is where things get tricky, because you can't just add velocities together like simple numbers. Motion in different directions doesn't stack up in a straightforward way. You need to use vector addition, combining both the speed and direction of each component of motion. Let's break it down layer by layer. First, you have Earth's rotation. If you're at the equator, that's about 1,000 miles per hour eastward. Then you add Earth's orbital motion around the Sun, which contributes roughly 67,000 miles per hour. But this motion changes direction throughout the year. Sometimes it adds to our galactic motion, sometimes it subtracts from it, and sometimes it's perpendicular to it. Next comes the Sun's orbit around the Milky Way, contributing approximately 447,000 miles per hour. This motion is roughly in the plane of the galaxy, carrying us in a giant circle that takes 230 million years to complete. Then there's the Milky Way's motion toward Andromeda, adding about 250,000 miles per hour. The local groups fall toward the Virgo cluster, contributes another 810,000 miles per hour. When you combine all these motions vectorially, accounting for their different directions, you end up with that final number we measured from the cosmic microwave background, roughly 827,000 miles per hour, or 370 kilometers per second. That's our net motion through the universe, the sum total of all these cosmic currents carrying us through space. But here's something that will really make you think, that 827,000 miles per hour isn't constant. It changes slightly over time as Earth orbits the Sun, as the Sun moves through the galaxy, as the Milky Way dances with Andromeda. Our cosmic velocity is dynamic, shifting subtly with the rhythms of the heavens. In fact, scientists have detected a small biannual variation in our velocity relative to the CMB. As Earth swings around the Sun, sometimes our orbital motion adds to our cosmic velocity, boosting it by about 30 kilometers per second. 6 months later, when we're on the opposite side of our orbit, that same motion subtracts from our total speed. It's a tiny oscillation compared to our overall speed, but it's measurable with precise instruments. Over much longer timescales, our motion changes even more dramatically. Remember, the Sun takes 230 million years to orbit the galaxy. During that journey, our velocity relative to the galactic center is constantly changing direction. We're moving in a huge circle, which means we're constantly accelerating, constantly changing the direction of our motion, even though our speed stays roughly constant. And here's something mind-blowing. During that 230 million year journey around the galaxy, we also bob up and down through the galactic plane. The solar system doesn't stay perfectly level with the disk of the Milky Way. Instead, we oscillate above and below the galactic midplane, completing about 2.5 vertical oscillations during each galactic orbit. Right now, we're slightly above the galactic plane, moving upward at about 7 kilometers per second. This vertical motion has real consequences for life on Earth. Every 30 to 35 million years, we pass through the densest part of the galactic disk, where there's more dust, gas, and higher rates of star formation. Some scientists have speculated that these passages might correlate with mass extinction events on Earth, though the evidence is still debated. The idea is that passing through dense regions might disturb the Oort cloud, a shell of icy bodies surrounding our solar system, sending comets plunging toward the inner planets. Speaking of the Oort cloud, even those distant frozen worlds located nearly a light year from the Sun are participating in all this motion. They're orbiting the Sun at just a few hundred meters per second, barely crawling compared to the speeds we've been discussing. But they're still being carried along on the Sun's galactic journey, still racing through the universe at hundreds of thousands of miles per hour. Now let's zoom back out and think about what all this motion means on cosmic scales. The fact that we're moving so fast through space has profound implications for our observations of the universe. When astronomers look at distant galaxies, they have to account for our motion. They need to subtract out our velocity to accurately measure how fast those galaxies are moving away from us due to the expansion of the universe. This becomes especially important when studying the cosmic microwave background. Once scientists removed the dipole pattern caused by our motion, they discovered something extraordinary: tiny temperature fluctuations across the sky, variations of only a few dozen millionths of a degree. These fluctuations are the seeds of all cosmic structure, tiny density variations in the early universe that eventually grew into the galaxies, clusters, and superclusters we see today. The COBE satellite first detected these fluctuations in 1992. The WMAP mission, launched in 2001, mapped them in unprecedented detail, and the Planck mission, which operated from 2009 to 2013, produced the most precise map yet. These missions have revolutionized our understanding of the universe. They've told us the age of the cosmos, 13.8 billion years. They've revealed the composition of the universe, about 5% ordinary matter, 27% dark matter, and 68% dark energy. But none of this would have been possible without first accounting for our motion through space. The dipole pattern from our velocity is thousands of times stronger than those tiny, primordial fluctuations. It's like trying to hear a whisper in a thunderstorm. Only by carefully removing the Doppler shift from our motion could scientists reveal the subtle patterns underneath. This illustrates a fundamental principle of astronomy. To understand the universe, we first have to understand ourselves. We need to know where we are, how fast we're moving, and in what direction. We're not outside observers looking at the cosmos from a privileged viewpoint. We're embedded in it, moving with it, part of the very thing we're trying to study. And that brings us to one of the most beautiful paradoxes in cosmology. Even though we're racing through space at nearly 1,000,000 miles per hour, even though we're part of this vast cosmic dance of galaxies and superclusters, the universe looks almost the same in every direction. This is called the cosmological principle, and it's one of the foundational assumptions of modern cosmology. The cosmological principle states that on large enough scales, the universe is homogeneous and isotropic. Homogeneous means it's the same everywhere. No location is special. Isotropic means it looks the same in all directions. Of course, this is only true when you zoom out far enough. On small scales, the universe is lumpy. There are planets, stars, galaxies, and galaxy clusters. But when you average over hundreds of millions of light years, those lumps smooth out into a uniform cosmic foam. This principle is remarkably well supported by observations. The cosmic microwave background, after removing our motion's dipole, is uniform to 1 part in 100,000 across the entire sky. Galaxy surveys show that the distribution of matter becomes increasingly uniform as you look at larger scales. By the time you reach scales of a few 100 million light years, the universe looks essentially the same in every direction. But here's the thing, if the universe is truly isotropic, if it looks the same in all directions, then every observer in every galaxy should see roughly the same thing. An astronomer in Andromeda would measure their own velocity relative to the CMB and find that they too are moving at hundreds of kilometers per second. An observer in a galaxy billions of light years away would make the same discovery. Everyone is in motion, no one is at rest. There is no center, no privileged location. This is the legacy of Copernicus and Galileo, extended to cosmic scales. We're not at the center of the solar system. The solar system isn't at the center of the galaxy. The galaxy isn't at the center of the universe. In fact, the universe has no center at all. Every point in space is equally valid, equally unremarkable, equally embedded in the cosmic web. And yet, despite this lack of a center, despite our tremendous velocity through space, there's structure and pattern everywhere we look. The universe isn't random chaos. It's organized on multiple scales, from planets to solar systems, to galaxies, to clusters, to superclusters. Gravity has been weaving this cosmic tapestry for nearly 14 billion years, turning tiny quantum fluctuations in the early universe into the magnificent structures we observe today. Our motion through space is part of that structure. We're flowing along gravitational currents that were set in motion by the Big Bang itself. The peculiar velocities of galaxies, their motion relative to the smooth expansion of the universe, trace out the invisible scaffolding of dark matter that holds everything together. By measuring how fast galaxies are moving and in what directions, astronomers can map the distribution of matter across cosmic scales. So how do scientists actually measure these cosmic velocities? How can we possibly know that we're moving at hundreds of thousands of miles per hour through space? It's not like there are cosmic speed limit signs floating in the void. The techniques astronomers use are ingenious, combining careful observations with deep physics, and they reveal just how far human ingenuity can reach. Let's start with the simplest measurement, Earth's rotation. This one has been known for centuries. You can actually measure it yourself with nothing more than a pendulum. In 1851, French physicist Léon Foucault suspended a heavy pendulum from the dome of the Pantheon in Paris. As the pendulum swung back and forth, he noticed that its plane of oscillation slowly rotated over the course of the day. This wasn't because anything was pushing the pendulum, it was because the Earth was rotating beneath it. The pendulum kept swinging in the same plane relative to the stars, but from our perspective on the rotating Earth, it appeared to turn. This elegant demonstration proved that Earth rotates, and by measuring how fast the pendulum's plane rotated, Foucault could calculate Earth's rotational speed. Today, we can measure Earth's rotation with extraordinary precision using atomic clocks and observations of distant quasars. We know Earth's rotational period to within microseconds. Measuring Earth's orbital speed around the Sun requires a different technique. One way is to observe the positions of nearby stars throughout the year. As Earth moves around its orbit, our perspective changes, causing nearby stars to appear to shift slightly against the background of more distant stars. This effect is called stellar parallax, and it's the same principle that makes your thumb appear to jump when you alternate closing your left and right eyes. By measuring how much a star's position shifts over 6 months when Earth has moved to the opposite side of its orbit, astronomers can calculate both the star's distance and Earth's orbital velocity. The ancient Greeks actually predicted this effect, but they couldn't detect it because stars are so incredibly far away that the shifts are tiny. It wasn't until 1838 that German astronomer Friedrich Bessel successfully measured stellar parallax for the first time, finally providing direct proof that Earth orbits the Sun. Today, missions like the European Space Agency's Gaia satellite are measuring parallax for over 1 billion stars with unprecedented precision. Launched in 2013, Gaia has created the most detailed three-dimensional map of our galaxy ever made. It can measure stellar positions to within millionths of an arcsecond, revealing the structure and motion of the Milky Way in exquisite detail. But measuring the Sun's motion around the galaxy is more challenging. We can't step outside the Milky Way and watch the Sun orbit from a distance. Instead, astronomers use the Doppler effect. When an object moves toward you, the light waves it emits get compressed, shifting toward the blue end of the spectrum. When it moves away, the waves stretch out, shifting toward red. By measuring how much starlight is Doppler shifted, we can determine how fast those stars are moving relative to us. Here's where it gets clever. Stars in different parts of the galaxy orbit at different speeds depending on their distance from the galactic center. By measuring the Doppler shifts of thousands of stars and combining that with their distances from Gaia, astronomers can build up a picture of how the galaxy rotates. This reveals not only the Sun's orbital speed, but also the distribution of mass in the Milky Way, including the dark matter halo that surrounds it. Radio observations are particularly valuable for this work. Hydrogen gas, the most abundant element in the universe, emits radio waves at a very specific frequency, 1420.4 MHz, corresponding to a wavelength of 21 centimeters. By mapping this 21 centimeter emission across the sky and measuring its Doppler shift, astronomers can trace the rotation of gas throughout the galaxy. These observations reveal spiral arms, stellar nurseries, and the complex dance of matter orbiting the galactic center. Measuring the Milky Way's motion toward Andromeda uses similar techniques. Astronomers observe the Doppler shift of light from stars in Andromeda and combine it with careful measurements of the galaxy's position over many years. Because Andromeda is so far away, it takes years of observations to detect its tiny motion across the sky. But by combining radial velocity, how fast it's moving toward or away from us, with proper motion, how it's moving across our field of view, scientists can calculate Andromeda's full three-dimensional velocity. Now here's where things get truly sophisticated. To measure our motion toward the Virgo cluster and the Great Attractor, astronomers use what's called the Tully-Fisher relation. This is a relationship between a galaxy's luminosity and its rotation speed. Faster rotating spiral galaxies are intrinsically brighter. By measuring how fast a galaxy rotates, which you can determine from its Doppler-shifted spectral lines, you can figure out how bright it should be. Compare that to how bright it appears, and you can calculate its distance. Once you know the distances and velocities of thousands of galaxies, you can map out their three-dimensional positions and motions. This reveals the flow patterns in the cosmic web, showing how galaxies are streaming toward dense regions and away from empty voids. Projects like the 2-degree Field Galaxy Redshift Survey and the Sloan Digital Sky Survey have mapped millions of galaxies, creating stunning three-dimensional maps of cosmic structure extending billions of light-years into space. But the most precise measurement of our cosmic velocity comes from the cosmic microwave background. The instruments used to detect this ancient radiation are marvels of engineering. They're incredibly sensitive, capable of detecting temperature variations smaller than a millionth of a degree, and they have to be. The entire sky glows with CMB radiation at about 2.7 Kelvin, just a hair above absolute zero. The dipole from our motion adds or subtracts only about 3 millikelvin from that temperature. The COBE satellite, launched in 1989, made the first precise measurement of the CMB dipole. Its instruments could detect temperature differences as small as 10 millionths of a degree. The mission confirmed that we're moving at about 370 kilometers per second relative to the CMB and mapped the direction of that motion to within a few degrees. WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001, improved on COBE's measurements significantly. Its instruments were 45 times more sensitive, and it observed the sky from a special location called the L2 Lagrange point, about 1 million miles from Earth on the side opposite the Sun. From this vantage point, WMAP could observe the CMB without interference from Earth's radiation or the Sun's heat. Then came Planck, the most sophisticated CMB observatory ever built. Named after physicist Max Planck, one of the founders of quantum theory, this European Space Agency mission operated from 2009 to 2013. Planck measured the CMB temperature across the sky with extraordinary precision, pinning down our velocity to within just a few tenths of a kilometer per second. Its final data release, published in 2018, represents the pinnacle of our current understanding. The technology aboard these satellites is breathtaking. Planck's instruments operated at just 1/10 of a degree above absolute zero, colder than the CMB itself. To achieve this, the spacecraft used multiple stages of cooling, including mechanical coolers and liquid helium. The detectors were so sensitive they could register the arrival of individual photons, particles of light that had been traveling through space for over 13 billion years. Think about what that means. A photon emitted when the universe was 380,000 years old, racing through space at the speed of light for eons, finally encounters a detector built by curious primates on a tiny planet orbiting an ordinary star. That photon's wavelength, stretched by the expansion of the universe from visible light to microwaves, carries information about the early cosmos. And by measuring thousands of these photons from every direction in the sky, scientists can reconstruct what the universe was like at its birth. But here's what amazes me most: the precision of these measurements keeps improving. Each new mission, each technological advance, reveals the universe in finer detail. When COBE first detected the CMB fluctuations in 1992, it could only see variations on angular scales larger than about 7 degrees. That's 14 times the size of the full moon. WMAP could detect features as small as about 1/4 of a degree. Planck pushed that down to about 5 arc minutes, 1/10 of a degree. This progression isn't over. Right now, ground-based observatories like the Atacama Cosmology Telescope in Chile and the South Pole Telescope in Antarctica are making even more detailed measurements of the CMB at smaller angular scales. These experiments are searching for subtle effects that Planck couldn't detect, like the imprint of gravitational waves from the Big Bang or the influence of massive galaxy clusters on the CMB photons passing through them. There are also exciting missions on the horizon. NASA and other space agencies are planning next-generation CMB satellites that will be even more sensitive than Planck. These missions aim to detect the faint polarization patterns in the CMB caused by primordial gravitational waves, ripples in space-time generated by cosmic inflation, a brief period of exponential expansion in the first fraction of a second after the Big Bang. Now let's explore something truly fascinating. What are the consequences of moving through space at nearly 1,000,000 miles per hour? You might think that such tremendous velocity would have obvious effects, that we'd feel some cosmic wind in our faces or experience strange physical phenomena. But the reality is both more subtle and more profound than you might imagine. First, let's talk about relativity. According to Einstein's special theory of relativity, motion affects the passage of time. The faster you move, the slower time passes for you relative to someone at rest. This effect is called time dilation. At everyday speeds, it's completely negligible, but as you approach the speed of light, it becomes dramatic. At 90% of light speed, time slows down by about half. At 99%, it slows to about 1/7. So what about our cosmic velocity? We're moving at roughly 370 kilometers per second through the CMB. That sounds fast, but remember, the speed of light is about 300,000 kilometers per second. We're moving at only about 1/8 of 1% of light speed. At that velocity, time dilation is absolutely tiny, only about 1 part in 200 million. If you spent a year at rest relative to the CMB while Earth continued its cosmic journey, you would age about 0.16 seconds more than someone on Earth. Completely unmeasurable in practice. But here's what's interesting. Different galaxies are moving at different speeds through the CMB. Some are moving faster than us, some slower. In principle, this means time passes at slightly different rates in different galaxies. An observer in a galaxy moving at, say, 600 kilometers per second through the CMB would experience time passing infinitesimally slower than we do. Over the entire age of the universe, they would have aged perhaps a few thousand years less than us. Still tiny, but theoretically real. This raises a philosophical question. Is the cosmic microwave background a kind of universal clock? Does it define a preferred reference frame for measuring time across the cosmos? Most physicists would say no. Relativity tells us that all inertial reference frames are equally valid. There's no privileged perspective, but the CMB does provide a natural reference point, a way to compare the passage of time across cosmic distances. It's a practical, if not fundamental, universal timekeeper. Another consequence of our motion is more directly observable: the aberration of starlight. This is a phenomenon first discovered in 1729 by English astronomer James Bradley. He noticed that the apparent positions of stars shift slightly depending on Earth's velocity. It's similar to how rain appears to fall at an angle when you're driving, even though it's actually falling straight down. The faster you drive, the more the rain seems to slant toward you. The same thing happens with starlight. Because Earth is moving around the Sun at 30 kilometers per second, the light from stars appears to come from slightly different directions depending on where Earth is in its orbit. This effect, called stellar aberration, causes stars to trace out tiny ellipses in the sky over the course of a year. The maximum displacement is about 20 arcseconds, roughly the size of a basketball, seen from 10 miles away. But there's also a much smaller aberration caused by the Sun's motion through the galaxy and our overall motion through the CMB. Every star's position is very slightly displaced in the direction of our cosmic motion. This displacement is only about 40 microarcseconds, far too small to detect with traditional telescopes, but missions like Gaia are precise enough to measure it. In fact, by carefully analyzing stellar positions across the entire sky, astronomers can independently confirm our velocity through space. Our cosmic motion also affects observations of the cosmic microwave background itself in subtle ways. Remember that dipole pattern we discussed? It's not just a simple hot spot in one direction and a cold spot in the opposite direction. There are actually higher order effects as well. Because we're moving so fast, the CMB photons get aberrated just like starlight. This causes a slight compression of the CMB pattern in the direction we're moving and a stretching in the opposite direction. There's also an effect called Doppler boosting. Photons coming from the direction we're moving toward get blue shifted and boosted in intensity, while photons from behind get red shifted and dimmed. This creates not just a temperature dipole, but also an intensity dipole. Planck detected both effects and found they matched Einstein's predictions perfectly. It's yet another confirmation of relativity, tested using the oldest light in the universe. But perhaps the most profound consequence of our cosmic motion is what it tells us about the nature of space itself. You see, when we say we're moving at 827,000 miles per hour through space, what exactly does that mean? What is space? Is it a physical substance that we're moving through? Or is it just the relationships between objects? This question has puzzled physicists for centuries. Newton believed in absolute space, a kind of invisible stage on which the universe plays out. Einstein rejected this idea, arguing that space and time are not separate entities but woven together into a single fabric called space-time. In general relativity, space-time isn't just a passive background. It's a dynamic entity that curves in response to matter and energy. Our motion through the cosmic microwave background suggests something interesting. The CMB provides a kind of cosmic lattice, a reference frame defined by the radiation left over from the Big Bang. This frame is special not because physics works differently in it, but because it represents the average rest frame of all the matter and energy in the universe. When we measure our velocity relative to the CMB, we're really measuring our motion relative to the universe as a whole. Think of it this way. Imagine you're floating in the ocean. You can measure your velocity relative to the water around you. The water isn't absolute space, but it provides a local reference frame. Similarly, the CMB provides a cosmic reference frame. It's not absolute, but it's universal. Every observer, no matter where they are in the universe, can measure their velocity relative to the CMB and compare it to ours. This has practical implications for cosmology. When astronomers measure the redshift of distant galaxies to determine how fast the universe is expanding, they have to correct for our motion through the CMB. The expansion of the universe causes galaxies to recede from us, but our local motion adds an extra component to their apparent velocity. By subtracting out our motion, scientists can isolate the pure cosmological redshift, the expansion of space itself. And here's something remarkable. The expansion of the universe is completely different from our motion through it. When we move through space at 827,000 miles per hour, we're traveling through existing space. But the expansion of the universe isn't motion through space, it's the stretching of space itself. Distant galaxies aren't moving away from us through space, the space between us is growing. This distinction is crucial. Our motion through the CMB could, in principle, be stopped. If we fired powerful enough rockets in exactly the right direction for long enough, we could bring ourselves to rest relative to the CMB. We'd no longer see the dipole pattern. Of course, this is completely impractical. It would require more energy than exists in the solar system, but it's theoretically possible. The expansion of the universe, on the other hand, can't be stopped by local motion. It's happening everywhere simultaneously. Every region of space is expanding, Galaxies separated by vast distances are being carried apart by this expansion, and the farther apart they are, the faster they recede. Galaxies beyond a certain distance are receding faster than the speed of light. Not because they're moving through space faster than light, which would violate relativity, but because the space between us is expanding that rapidly. This leads to one of the most profound realizations in cosmology. There are galaxies we will never be able to see, no matter how powerful our telescopes become. Their light is trying to reach us, racing through space at 300,000 kilometers per second, but the expansion of the universe is carrying them away faster than their light can travel toward us. They're beyond something called the cosmic horizon, and they're forever out of reach. Currently, the observable universe has a radius of about 46.5 billion light-years. That's how far light has been able to travel toward us since the Big Bang, accounting for the expansion of space. But the actual universe is almost certainly much larger than this, possibly infinite. There could be countless galaxies, stars, and planets beyond our cosmic horizon, entire regions of space that we will never observe. And here's the kicker: because the expansion of the universe is accelerating, driven by something called dark energy, the observable universe is actually shrinking in a sense. Galaxies that we can see now will eventually cross the cosmic horizon and disappear from view. In the far future, trillions of years from now, an observer in our galaxy would see a much emptier universe. Most galaxies would have receded beyond the horizon, and the only stars visible would be those in our local group of gravitationally bound galaxies. This is one of the strangest things about living in an expanding universe. We're actually in a privileged time to study cosmology. We can still see distant galaxies, still measure the cosmic microwave background, still piece together the history of the universe. Future civilizations, if they arise, will have a much harder time. They'll look out at the cosmos and see mostly darkness, with no evidence of the Big Bang, no distant galaxies to study, no way to know that the universe is expanding. Our cosmic motion, then, is intimately tied to the expansion and evolution of the universe itself. We're not just moving through space, we're participants in a cosmic drama that began nearly 14 billion years ago and will continue for trillions of years into the future. Every motion from Earth's rotation to the local group's journey through the cosmic web is part of this grand narrative. Right now, at this very moment, scientists around the world are making breakthrough discoveries about our motion through the cosmos. New telescopes, new satellites, and new techniques are revealing details that were unimaginable just a few years ago. Let's explore the cutting edge of cosmic velocity research and the fascinating mysteries that remain unsolved. One of the most exciting developments comes from the Gaia mission. Since its launch in 2013, Gaia has been systematically measuring the positions, distances, and motions of over 1 billion stars in our galaxy. Every few months, the mission releases new data, and each release transforms our understanding of the Milky Way. The most recent data release, called Gaia DR3, published in June 2022, contains measurements so precise they're almost unbelievable. Gaia can measure a star's position to within millionths of an arc-second. To put that in perspective, imagine standing in New York City and measuring the width of a human hair in Los Angeles. That's the level of precision we're talking about. And it's not just positions. Gaia measures proper motion, how stars are moving across the sky, to similar precision. This allows astronomers to trace the orbits of stars backward and forward in time, revealing the history and future of our galaxy. These measurements have uncovered something extraordinary. The Milky Way is far more dynamic than anyone realized. Stars aren't simply orbiting smoothly around the galactic center. Instead, they're participating in complex patterns of motion caused by past collisions with smaller galaxies. When a dwarf galaxy merges with the Milky Way, its stars get scattered and stretched out into streams that persist for billions of years. Gaia has detected dozens of these stellar streams, each one telling the story of an ancient cosmic collision. One particularly dramatic discovery is called the Gaia Sausage. About 10 billion years ago, a dwarf galaxy containing tens of billions of stars crashed into the Milky Way. The collision scattered stars in all directions, creating a sausage-shaped distribution of orbits. Today, we can still see the remnants of this collision. Stars in the Gaia Sausage have distinctive velocities and chemical compositions that set them apart from stars born in the Milky Way itself. These discoveries matter for understanding our cosmic motion because they reveal that galaxies aren't static objects. They're constantly evolving, constantly merging and interacting. The Milky Way we see today is a palimpsest, layer upon layer of history written in the motions of stars. Our Sun's current orbit through the galaxy was influenced by these past collisions, and future mergers will change it again. And speaking of future mergers, Gaia is providing unprecedented detail about the Milky Way's approaching collision with Andromeda. By measuring the proper motion of stars in Andromeda with extreme precision, astronomers can now predict the trajectory of the collision with remarkable accuracy. The current best estimate suggests that Andromeda will make its closest approach in about 4.5 billion years. But here's what's new. Gaia data suggests the collision might be more of a glancing blow than a head-on impact. Instead of smashing directly into each other, the Milky Way and Andromeda might sidesweep initially, then swing around and collide more directly later. The entire process could take several billion years, with multiple passages before the two galaxies finally settle into a single merged system. What will that merged galaxy look like? Simulations suggest it will be an elliptical galaxy, a vast swarm of stars with little organized rotation and no spiral arms. It's been nicknamed Milkomeda, or sometimes Milkdromeda. By the time it forms, our Sun will likely be in its red giant phase, possibly having already consumed Earth. But if any planets survive in the habitable zone, observers there would witness a sky full of stars with completely different arrangements than we see today. Meanwhile, other cutting-edge research is focusing on those mysterious, large-scale flows we discussed earlier. Remember the Great Attractor and the Shapley supercluster? New galaxy surveys are mapping these structures in unprecedented detail. The Taipan survey in Australia and the DESI survey in Arizona are measuring the distances and velocities of millions of galaxies, creating three-dimensional maps of cosmic structure that span billions of light years. These surveys have confirmed something puzzling. There really do appear to be bulk flows in the universe that extend farther than our models predict. When you look at the motions of galaxy clusters hundreds of millions of light years away, you find they're moving in coherent patterns as if being pulled by something beyond what we can see. This is sometimes called the dark flow, and it's one of the most controversial topics in cosmology today. Some scientists argue that dark flow is evidence of structure beyond our observable universe, massive concentrations of matter so far away their light hasn't reached us yet, but whose gravitational influence can still be felt. If true, this would be our first evidence of what lies beyond the cosmic horizon, a tantalizing glimpse of the unobservable universe. Other scientists are more skeptical. They point out that measuring the peculiar velocities of distant galaxies is extremely difficult and prone to systematic errors. It's possible that the apparent dark flow is just an artifact of how we're analyzing the data, not a real physical phenomenon. The debate continues, with new observations and new analysis techniques being developed to settle the question. Another mystery involves something called the CMB cold spot. Remember how the cosmic microwave background is almost perfectly uniform after you remove the dipole from our motion? Well, there's one region of the sky about 5 degrees across that's significantly colder than the surrounding area. It's about 70 microkelvin colder than average, which doesn't sound like much, but it's statistically unusual enough to raise eyebrows. Several explanations have been proposed. Maybe it's just a random fluctuation, a statistical fluke that happened to occur in the early universe. Maybe it's caused by an enormous supervoid, a region of space with fewer galaxies than average, which would create a cold spot through something called the integrated Sachs-Wolf effect. Or, more speculatively, maybe it's evidence of something truly exotic, like a collision between our universe and another universe in a multiverse scenario. Current observations favor the supervoid explanation. Surveys have indeed found a large, underdense region in the direction of the cold spot, but the supervoid doesn't seem quite big enough to fully explain the temperature anomaly, so the mystery isn't completely solved. Further observations are needed, and several missions are planned to study the cold spot and other anomalies in the CMB with even greater precision. Then there's the question of whether our cosmic velocity is truly constant, or if it changes over time. We know it fluctuates slightly due to Earth's orbit and the Sun's galactic motion, but could there be larger, slower variations? Could the local group's velocity through the CMB be gradually increasing or decreasing as the large-scale structure of the universe evolves? Some theoretical models suggest this might be possible. As dark energy drives the accelerating expansion of the universe, it affects the growth of cosmic structure. Galaxy clusters that are currently forming might stop growing and begin to disperse. This could change the pattern of gravitational flows, potentially altering our cosmic velocity over timescales of billions of years. Testing this hypothesis requires extremely precise measurements over long periods. We need to compare CMB observations taken decades apart to see if the dipole pattern has shifted. So far, the data from COBE, WMAP and Planck are consistent with a constant velocity, but the time baselines are still relatively short. Future missions observing over many decades will provide a definitive answer. There's also fascinating work being done on what's called velocity caustics. These are sharp features in the velocity field of the universe, places where the flow of galaxies changes direction abruptly. They form at the boundaries between different large-scale structures, like the edge of a supercluster or the wall of a cosmic void. By mapping these caustics, astronomers can trace out the skeleton of the cosmic web with incredible detail. One particularly interesting caustic surrounds the local group itself. There's a shell of galaxies about 5 million light-years away that marks the boundary between regions falling toward us and regions being carried away by the expansion of the universe. This is called the zero-velocity surface, and it defines the gravitational sphere of influence of the local group. Everything inside this boundary will eventually merge with either the Milky Way or Andromeda. Everything outside will recede from us forever. Understanding these boundaries is crucial for cosmology because they reveal how dark matter is distributed on cosmic scales. Dark matter doesn't emit light, so we can't see it directly. But we can infer its presence from how it affects the motion of galaxies. By carefully mapping peculiar velocities across large volumes of space, scientists can create three-dimensional maps of dark matter distribution, revealing the invisible scaffolding that holds the universe together. And here's something that absolutely blows my mind. Some researchers are even trying to use gravitational waves to study cosmic motion. Gravitational waves are ripples in space-time caused by violent cosmic events like merging black holes or neutron stars. When LIGO and Virgo detect these waves, they can measure properties like the masses of the merging objects and the distance to the event. But here's the clever part. Gravitational waves also carry information about motion. If a source of gravitational waves is moving relative to us, the waves get Doppler shifted, just like light. By measuring this Doppler shift and comparing it to the optical redshift of the galaxy hosting the event, scientists can determine that galaxy's peculiar velocity. This provides an independent way to map cosmic flows, complementing traditional techniques. This field is still in its infancy. We've only detected a few dozen gravitational wave events so far, not enough to draw firm conclusions about cosmic flows. But as detectors improve and we detect hundreds or thousands of events per year, gravitational wave cosmology could become a powerful new tool for understanding our motion through the universe. If you made this far, I am sure you will love this other video at the left side of the screen. Why it's impossible for humans to travel 1 light year. 1 light year is an insurmountable wall, and that's why we are so alone. Not because aliens don't exist, but because the universe has made sure we can never reach them. See you there.